In the last lecture, we discussed about the free electron model, which gives a good insight into many properties of metals, such as the heat capacity, thermal conductivity, and electrical conductivity. However, this model fails to help us other important properties. For example, it does not predict the difference between metals, semiconductors, and insulators. It does not explain the occurrence of positive values of the Hall coefficient. Why are some materials insulators, some metals? What is a semiconductor? What makes them useful? In the free electron model, the dispersion is shown in equation 1. The corresponding eigenfunctions psi are plane waves with a real space representation. Psi is proportional to e to the power ik.r. We note that in the free electron model, there is only one band. The band structure is not periodic in K-space. i.e., the Brillouin zone is infinite in K-space. We must extend the free electron model to take account of periodic lattice of solid. The possibility of bandgap is the most important new property that emerges. The nuclei are arranged in a periodic crystalline array. This changes the energies of the electrons and leads to different behavior in different crystals. Electrons respond to applied electric or magnetic field as if provided with effective mass, which can be larger or smaller than free electron gas or may even be negative. Electrons in crystals respond to applied electric field as if endowed with negative or positive charges. This causes the negative and positive values of Hall coefficient. The nearly free electron model is a quantum mechanical model of physical properties of electrons that can move almost freely through the crystal lattice of a solid. Here, the band electrons are treated as perturbed only weakly by the periodic potential of the ion cores. We know that Bragg reflection is a characteristic feature of wave propagation in crystals. Bragg reflection of electron waves in crystals is the cause of energy gaps. At Bragg reflection, wave-like solutions of the Schrödinger equation do not exist. See figure on next slide. These energy gaps are of decisive significance in determining whether a solid is an insulator or a conductor. Consider 1D linear lattice to explain origin of energy gaps. The Bragg diffraction condition is n lambda is equal to 2 a sin theta. Where is the lattice spacing? In reciprocal lattice, the Bragg condition is k plus g. The whole square is k square for diffraction of a wave vector k. K is equal to plus or minus half g, where g is 2n pi by a, where n is an integer. The first reflections and the first energy gap occur at k equal to plus or minus pi by a. The region in K space between minus pi by a and plus pi by a is the first Brillouin zone of this lattice. Other energy gaps occur for other values of the integer n. At these special values of k, the wave function are made up of equal part of wave traveling to left and right. At Brillouin boundary, the wave function reflected back to the opposite direction. Hence standing waves, a wave that does not travel to the right or left, is formed. There are two standing waves, psi plus and psi minus, depending on the combination of two traveling waves. Psi plus sign is invariant when x is replaced by x, whereas in psi minus, the sign changes. The two standing waves pile up electrons at different regions. Hence they have different values of potential energy. This results bandgap. The probability density and hence charge density is constant in the case of free electron, where ρ is equal to psi star psi, that is equal to e to the power x into e to the power minus x, which is 1. But for psi plus wave this charge density is proportional to cos square pi x by a. This function pile up electron at positive ion cores. Similarly, for the psi minus wave function the probability density is proportional to sin square pi x by a, which concentrates electron away from the ion cores. The figure 3 shows variation of electrostatic potential energy of conduction electron in field of positive ion cores. The charge density in the case of free electron is compared with those of psi plus and psi minus standing waves. When we calculate the average or expectation values of the potential energy over these three charge distributions, we find that the potential energy of ρ plus is lower than that of the traveling wave, whereas the potential energy of ρ minus is higher than the traveling wave. We have an energy gap of width e.g. just below the energy gap at point A in Fig 2. See slide 5, the wave function is psi plus, and just above the gap at points B the wave function is psi minus. To find the magnitude of energy gap, we write the potential energy of an electron in the crystal at point X as roughly as U, X, is equal to minus U cos 2 pi x by a. The first order energy difference between the two standing wave states is obtained by integrating U, X, multiplied by difference in probability density from 0 to a. We will see that the gap is equal to the Fourier component of the crystal potential. Hence in this lecture we consider nearly free electron model to explain the band gap in solids. We see that due to Bragg diffraction standing waves formed at the zone boundaries. This will form energy gap.